Yeah, that looks really nice. Do you have any movies or anything you want to check, or is it all good?
No, they're all static slides, unfortunately, so I think it
Oh,
should
it's
be
all good.
okay.
Don't say unfortunately. Movies are always a technical issue, so that's good. Okay. Um, so who was the? Maybe we should just test the second one. So if you can relinquish screen for a sec.
Yep.
And, I am the co-host. Not sure if that's a good thing, but all right. Okay, so can we put up the slide for the um, for the program, please? I don't know where our court-appointed helper went, but anyway.
The next speaker is Adam Fu.
Oh, yeah. Oh, so how are you doing that, Adam? Do you just put up the? Sorry, it just fills my screen. So.
I was just looking at the schedule online.
Yeah. No, okay, I got it. I was just behind. Okay, so yeah, Adam and then Manfred. Adam, are you here or not? Not Adam Monahan, Adam Fu. Okay, exciting. How come you got the good session, Adam? Manfred Nightham, are you here? Okay, they're not here.
So I just realized that this Zoom meeting is actually different from the last Zoom meeting we were in.
Yeah.
I mistakenly went to the old one, so
Yeah.
I wonder if some people have done that. Yeah.
I think we should give people a minute.
Let's give them a minute. Yeah. Yeah. Take a look further down the list. So I saw a Zoom handle, Becca Boitel. I'm sure I'm mispronouncing it. I saw you, right? You're there? Yeah. Okay, that's good. So we do have some speakers. Ajay Ravindran. And then, well, Paul's always trouble. He'll be here. I feel he'll be here at some point. Okay, so again, do we have any of the speakers in the middle? Adam Fu, Manfred Nightham, Jackie Chen.
Yes, I am.
Okay, good. So so we're just missing the second and the third. So maybe we'll give them time to drift in. So why don't I don't know. What do you guys think? Maybe a couple more minutes? I mean, I don't want to go super overtime because it's getting late. Oh, there's Adam Fu.
I think we can probably get going.
Okay, so welcome everybody. So my name is Mark Stasna. I am one of the co-organizers for this session. This is 4041 Atmosphere, Ocean, and Climate Dynamics. And same setup as before. So, try to stick to time. And, we'll remind you if we need to, and then questions in the chat or speak up. And yeah, we'll get through it and we'll have some fun. So the first talk is by Romina Puno, and you can grab a screen and take it away.
Great, thanks. So, all right, yeah, here we are. My name is Romina. I'm from the University of Toronto, and I've been looking at the sensitivity of convective overturning and turbulent mixing of dissolved gases in the Labrador Sea to atmospheric forcing. So to motivate this, the oceans are the largest sink of anthropogenic carbon, absorbing about a third of all atmospheric CO2. And so typically where gases remain at flux with the surface, so any dissolved gases from the atmosphere wind up in the first few meters of the ocean, and they kind of stay there. But that's an exception in a few places, one of which is in the Labrador Sea, where deep convection is able to sequester those surface waters in excess of 2 kilometers in depth. And so that's really impressive, and that happens over a matter of a few days, so it's really quick as well. And so what that does is it refreshes the surface layer's ability to uptake more carbon. So before we jump into things, I want to start by, there we go. I want to start by talking about the North Atlantic Oscillation, because it's been well documented that the NAO has an effect on this deep convection in the Labrador Sea. So I think it's important to, talk about what it is and what it means for convection in the Lab Sea. So it's so the North Atlantic Oscillation is just that, it's an oscillation, and it's computed from principal component analysis. But the important thing to remember here is that it ultimately describes the pressure gradient between two centers of action. That's the Icelandic low and the Azores high over here. And so a large positive index means above average sea level pressures above the Azores and below average sea level pressures over Iceland and vice versa. So ultimately, again, it describes the strength of that pressure gradient. So a strong positive index, which is that left figure, corresponds to cold temperatures in Greenland and warm temperatures in Scandinavia. And that is a result of the strong zonal flow across the North Atlantic that's depicted there. And ultimately in the Labrador Sea, the NAO favors these cold, dry winds which blow off the Canadian continent that favors convection there. And I'll also be using pressure data from the northern center of action, the Icelandic low, on its own as its own index. And these data are collected in situ. There. Come on, next slide, please. There we go. Okay, so then that begs the question, what modulates convection in the Labrador Sea, right? It's, like I said, it's been well documented that the effect of the NAO that the NAO does modulate convection in the Lab Sea. But here I'm going to present evidence to support the notion that it's the northern center of action, the Icelandic low, that has a greater modulating factor of this convection here, simply by virtue of proximity. So to study this, I'll be using the ERA5 reanalysis data set. And so it's exactly that, a reanalysis data product, and that offers hourly data at a 30-kilometer resolution. And from this, I'll be deriving the net heat flux, which I'm taking as the sum of latent and sensible heat fluxes along with long and short wave radiation. And so I've added all of those together, and then we get this net heat flux field. So moving on. So yeah, I've plotted each of those as time series. So I have the NAO time series, the Icelandic low time series. I've standardized that index. So I've subtracted the mean and divided by the standard deviation. And I'm going to be comparing those against the net heat flux. And so here we aim to assess the degree to which large scale atmospheric modes of variability force deep convection in the Lab Sea. So again, specifically the NAO, its northern center of action, the Icelandic low, and the net heat flux. And so what ends up happening, right? The oceans are heated from above by the sun. And so that leaves this warm, less dense layer at the surface and colder, more dense waters underneath it. And so if we want to trigger overturning, there needs to be sufficient cooling to that surface layer in order to compromise that stability. And so this is why to first order ocean convection relies on the net surface heat flux. So the third time series, again, is taken as the ideal case for triggering ocean convection for this reason. And so the NAO and Icelandic low indices will be contrasted against the net heat flux. I've also highlighted the 5 most extreme values, so the 5 greatest and 5 lowest values in each of those time series. And so what I've done from that is, given all of those years, the 5 highest and the 5 lowest years, I've computed composites of those. And so I have taken the difference between those composites, so the highest minus the lowest, and we end up with something like this. I should also mention that the black box highlighted on each of those figures is where convection is most active. So the composite fields indexed by the NAO index and the Icelandic low show the strongest signal along the western marginal ice zone. And so what's happening is that sea ice insulates against thermal fluxes. However, it also cools winds which blow off from the dry continent, and that favors the cooling of adjacent waters. And likewise, strong winds along the east coast of Greenland favor oceanic cooling along the coast as well. So we're seeing this strong signal along the marginal ice zone. So I think it's worth looking into sea ice concentrations as well. So there we go. So like I said, sea ice acts to insulate against these cold, acts to insulate the cold atmosphere from the underlying warm ocean, making the rate of energy and momentum transfer between the air and sea sensitive to sea ice concentration. So when leads or polynyas open up within the ice, it exposes the underlying water, yielding a steep temperature gradient, which facilitates these elevated heat fluxes. And so it's for this reason also that fluxes are most intense near the ice edge. Okay, this is all great, but how does it translate into deep convection? So to study this, I've employed a simple one-dimensional ocean model named PWP after its authors to gauge the Labrador Sea's response to surface fluxes of heat, salinity, and momentum. So this model was originally designed in 1986 to study the response of the upper ocean layers to diurnal cycling of solar insolation and wind mixing. But since then, it's been shown capable of capturing major oceanic responses to thermal fluxes and wind mixing, and the impact of these fluxes on vertical convection. So I'll be using PWP to investigate how the mixed layer depth evolves over the course of about half a year, from October through to the end of March. The way that this model works from a very high level is that it applies these fluxes at the surface. So that's fluxes of heat, momentum, freshwater tracers, what have you. And then it mixes to relieve those static and shear flow instabilities that arise from those fluxes. And so ultimately the model assumes that the profile is stable at the end of every time step. Okay, so we have this model, we need to initialize it with something. And so what's shown over here, each of these gray lines is an individual Argo density profile taken from that deep convection zone that I've highlighted in the previous plots where that black box was. And these are from years 2001 to 2020. And so we can see, I should also mention that the red line is the mean of each of those of each density profile. And so the mean is what I'm going to be using to initialize my PWP model. And the red shading is plus or minus 1 standard deviation, just to give you an idea of what the variability looks like there. And so what we can see here is that the profile is fairly stable at the beginning, in October, November, and December, and where stability is defined as increasing density with depth. So we can see that with depth, the density increases rather rapidly at the surface, but then that stability begins to break down as we move into January and February. So the PWP model was run from the 1st of October through to the 31st of March for every year from 1950 to 2020. And it was forced with the ERA 5 reanalysis product. And like I said, the model was initialized using the same mean October profile from in situ measurements taken by Argo floats within the deep convection zone between those years 2001 to 2020. So that's this red profile right here. That's what I'm using to initialize my model. So Argo only goes back to about 2001, 2002. And so it's important to remember that I'm not trying to recreate past conditions. I'm simply using the same profile to gauge the sensitivity of the mixed layer depth to various atmospheric forcing conditions. All right, so after I run all of those models or those iterations of that model, this figure over here shows the evolution of the mixed layer depth throughout the modeled fall and winter seasons. So the red curve is the mean of all model runs from 1950 to 2020, with the shading highlighting the 1 standard deviation range. A similar compositing approach was used to investigate the mixed layer deepening under different atmospheric forcing conditions. So composites of the 5 most extreme years were shown in blue and green. So that's of the NAO, Icelandic low, and net heat flux that I showed on those previous slides highlighted with those little orange dots. And so what we can see is a clear difference is shown in the figure where the NAO index is large and the mixed layer. So when the NAO index is large, the mixed layer deepens earlier, following the climatological mean throughout most of the modeled season. However, when the NAO index is small, the mixed layer entrainment happens more than a month later in the season. And this trend is similar to that case, composited by the most extreme net heat flux that's also shown. A large net heat flux shows mixed layer depth entrainment following the mean, whereas when the heat fluxes are low, the mixed layer entrainment happens later in the season. So this suggests that convection is triggered when a sufficient amount of heat flux is lost from the surface, and the degree of convection is not necessarily proportional to the heat flux. So it's more of like a binary triggering condition. So additionally, in both composites of the NAO and heat flux, a weak NAO index and low heat flux result in an early restratification of the water column. So composites of the Icelandic low extrema tend to follow the mean until late winter when the profiles begin to diverge. Generally, a strong Icelandic low yields a deeper mixed layer throughout the season than a weaker one, as well as an earlier onset of mixed layer entrainment. More notably between the two profiles is the final mixed layer depth. So a weak Icelandic low seems to allow for restratification by midwinter. Furthermore, while the NAO and the heat flux conditions which favor convection show a final mixed layer close to the mean. The strong Icelandic low case has a considerably deeper mixed layer by the end of the simulated winter. So just to sum things up, and this isn't working, there we go. Convection in the Labrador Sea entrains surface waters to more than 2 kilometers in depth. And the NAO and its northern center of action, the Icelandic low, favor cooling of the subpolar North Atlantic. The Icelandic low is a stronger modulating factor of Labrador Sea convection simply by virtue of proximity. And to study this, I used a one-dimensional ocean model to investigate the mixed layer sensitivity to large-scale atmospheric variability. A strong NAO would yield more severe but ephemeral weather conditions, whereas a strong Icelandic low tends to favor more persistent cooling and a deeper mixed layer by the end of the season. And with that, I'm happy to take any questions.
Thank you very much. And thank you for sticking to time. Do we have a question for Romina? I don't see anything in the chat yet. Okay, so maybe I'll have a quick one. So you talked about using Argo floats, right, for those gray plots you showed. You said you want them in the region of the deep water production. So how are you defining that? You know, Argos move around, right? So are you just kind of saying when they're in kind of a region that you want, you record that data? Is that what you're?
Yeah, exactly. So they bob up and down about every 10 days or so. And within that period, they don't tend to drift too far. So as long as the profile is within that, let me find, within this black box that I've highlighted, I've pulled that profile.
Perfect. That makes good sense to me. Okay, and there are no other questions in the chat, so maybe people will contact Romina offline. So thank you for a nice talk, and let's move on to the next one. Adam Fu, I guess, is the next speaker. So Adam, I saw you join earlier, so do you want to grab screen?
Yeah, I'm going to share my screen.
Excellent. So I'll mute myself and you can take it away.
Hello, everyone. My name is Adam. I'm a master's student from the University of Alberta. Today, my talk is about modeling the Atlantic water along its polar pathway into and through the Arctic Ocean. The Atlantic water is typically a warm and saline water mass originated from the North Atlantic Ocean. And this map shows the large-scale circulation of the Atlantic water inflow to the Arctic Ocean. And the Atlantic water enters the Arctic Ocean in two branches, Frame Strait branch water and Bering Sea branch water. As they converge into the Atlantic water boundary current, it flows further along the rim of the Eurasian basin. When it reaches the Lomonosov Ridge, it bifurcates into two branches. Here, we draw some cross sections at Frame Strait, the Bering Sea opening, and some along the margins of the Arctic basin to investigate how the Atlantic water alters as it propagates. For example, here, like at section 3, it documents the Atlantic water boundary current before the bifurcation. The simulations are conducted using the regional configuration of the ocean model, NIMO, running at 1/4 and 1/12 degrees horizontal resolutions, named ANA 4 and ANA 12, respectively. And near the Arctic gateways, it has the resolution of around 13 kilometers in ANA 4 and around 4 kilometers in ANA 12. The initial and open boundary conditions includes 3D ocean views, temperature, salinity, velocity, and 2D sea surface heights and sea ice views. And the atmospheric forcing adding on the sea surface includes 10-meter wind, 2-meter air temperature, specific humidity, total precipitation, as well as the long wave and short wave radiations. Here's the table showing the long-term means of the volume and heat transport through Frame Street and the Bering Sea opening from ANA 4, ANA 12, and the observations. The model results demonstrates general agreement with the observations. And at the Arctic gateways, the Bering Sea branch water plays a relatively larger role in bringing more heat into the Arctic than the Frame Street branch water, even though their volume transports are nearly equivalent, around 3 Sverdrup. And from the Atlantic water volume transport calculation at section 3, we notice true significant transport reduction. And farther along the pathway at section 6, the transport reverses in sign. And we originally considered whether the Atlantic water circulation has temporarily reversed. And after further study, we found that instead of reversing, the transport reduction at section 3 and the transport anomaly at section 6 are related to the existence of a colder water mass. We name it the cold Atlantic water. The cold Atlantic water keeps the Atlantic water's saline property, but with below 0 temperature. And we then calculate the cold Atlantic water volume transport. The pulses are clear in 2013 and 2014. The transport has increased following its polar pathway from Bering Sea to section 3 and reaches maximum at section 3. The cold Atlantic water replaces the regular Atlantic water and thus causes the reduction at section 3 during the corresponding time periods. And to identify the structure of the cold Atlantic water, like within an annual cycle, we plot the temperature field at Bering Sea, a section at St. Anna Trough. The cold Atlantic water lies over the slope of the eastern side and extends to the ocean bottom from March all the way to August. What are the physical mechanisms causing the cold Atlantic water formation? To address this question, we simulate the air-sea transformation for the cold Atlantic water in response to the surface heat and freshwater fluxes. The buoyancy fluxes produce transformation when the surface temperature, salinity meet the criteria of the cold Atlantic water. The figure on the left-hand side shows the transformation rate changing with the surface density in 2013. The positive values represent a removal of buoyancy, which means the water has been densified, and the heat, the surface heat flux has been dominant for the transformation. And the map in the middle demonstrates the spatial pattern of the transformation for the cold Atlantic water at a particular density bin where the transformation is pronounced. And it exemplifies that the cold Atlantic water mainly occurs in the Barents Sea. And this time series figure presents high transformation rates for 2 consecutive years, which are consistent with the cold Atlantic water pulses. Therefore, the sea surface cooling over these 2 years in the Barents Sea is the dominant contributor to the cold Atlantic water formation. And we apply REN and particle tracking product to probe the fate of the cold Atlantic water after passing through the St. Anna Trough. Nearly 2,000 particles are released at Barents 2 in July 2013. And after 50 days, the particles demonstrates a clear cascading process with some distributing near the basin edge and successively extending to the isobath of 2,000 meters. And this cascading process leads to a strong mixing or entrainment along its propagation way. To examine the impacts that the cold Atlantic water has on the Arctic basin, we calculate the heat content integrated the whole water column in this blue region, and the heat content quantifies the heat in the content in the Atlantic water layer, reference to 0 degrees, and the heat content has experienced a significant downturn right after the cold Atlantic water events in 2013 and 2014. So so it shows that the decline in the heat content is dictated by the cold Atlantic water signals propagating through this region. Here comes to our conclusion. The model results demonstrates general agreements with the observations in terms of long-term means of the Atlantic water volume and heat transport at these 2 Arctic gateways. And so we could use our ocean models to study questions related to the Atlantic water. And the sea surface cooling over these 2 years in the Barents Sea provides critical preconditioning for the transformation into the cold Atlantic water. The cold Atlantic water exhibits the cascading process as it propagates along the rim of the Eurasian basin, leading to a considerable mixing with the ambient water. And that's why we could see the maximum transport at section 3. And lastly, the cold Atlantic water pulses caused the heat content reduction in the Eastern Arctic Basin. And that's my presentation for today. Please let me know if you have any questions.
Okay, thanks. Sorry, I'm just letting some people in. So Natasha Ridnour has a question. Natasha, why don't you just ask your question?
Hi, Adam. How's it going? That was really interesting. So I guess I'm just wondering, I guess, is this a new water mass that has emerged because the Atlantic water can reach farther north in recent years with the reduction of sea ice?
Yeah.
So I guess more of my question is would it have happened in the past, or is it kind of a recent phenomenon, I guess?
Yeah, like from our study is the recent events because I only look at the years from 2011 to 2019. I haven't looked at the past, but and even like in the future, because right now we have the global warming, right? And under the context of the global warming, and we would have less sea ice in the Barents Sea, right? And then so the coupling between the atmosphere and the ocean will become more tight, and that's why we could like see the cold Atlantic water events because of the intensity surface cooling. And but in the past, maybe we also have this kind of events, but I'm not quite sure.
Okay.
Oh yeah, like yeah. Yeah, you're also asking me like what might happen in the future. So yeah, and that's like from one aspect, but also I just add one more thing, like even though we might has less sea ice and we have like more coupling between the atmosphere and the ocean, but because the air temperature is becoming warmer, so the temperature difference between the atmosphere and the ocean will be reduced in the future. So it really like depends which factor takes the dominant role. So yeah, we might expect more and more cold Atlantic water events in the future.
Okay, I think we should probably move on just so we all get to have supper at some point. So thanks, Adam. Next talk's by Manfred Nightham, and I'm not sure Manfred was here earlier. Are you here?
Yes, I'm here. Thank you.
Okay, awesome. So grab a screen whenever you're ready.
Okay, thank you. So my presentation today will be on the effects of currents, winds, river flow, and tide on salinity in James Bay. It is a part of a global project that we are carrying out in the James Bay with Niskamun and University of Quebec at Rimouski. Let me hide this thing. Okay. So first of all, our area of interest is the James Bay system, and it is a shallow bay, like the extension of the Hudson Bay to the south. But something that is very interesting about the system is that even if the water property and tides are forced from outside by the Arctic and the Atlantic Ocean, something that is very interesting for me is the fact that the property of water are mainly modified by the process in the bay. And the process in the bay includes some forcing. So for this, and the process in the bay include like ice, winds, river flow, current, tide, evaporation, and precipitation. This forcing has different impacts depending of the season. For example, in winter, it's very relatively different when we move on to summer with the dispersion of the ice at the surface of the water and the mixing due to the effect of the wind at the surface. Something that is very also characteristic of the system is that cyclonic circulation inside the depth that contribute to transport the salinity from the Hudson Bay inside the system and outside of the James Bay to the Hudson Bay again. But among the forces that we mentioned, one of them have been very modified this last year was the river discharge. The river discharge was modified by the construction of the hydroelectric complex to La Grande Rivière, which was made by the modification of some rivers like the Grand River by itself, the River Esmain, and the system of River of Rupert. So as you can see on this map, on this graph, the construction of the hydroelectric complex with the modification of some system has led really to the modification or the increase of the river flow to La Grande Rivière. But you agree with me that with this kind of modification of the water or the river discharge, the characteristic of the water will not be stay the same. So this kind of thing can have the impact for the local communities, especially here, where you find the native community, the community of Cree, will really depend on some local activity like hunting and fisheries. So with the modification of river discharge, many hypotheses were expressed this last year due to the modification of the population, of the quantity of hair glass in that system, the reduction of the activities, and really the modification of the way of life of the population. So in that project, in that aspect, the foundation Niskamon is the society there that wants to understand what is happening. So they are working with Hydro-Quebec, and if you move there, you also see that population are very concerned about what is happening. If you exchange with them, they will always tell you as a scientist that some years ago, we have hair glass here, today we don't have it again. So there are many questions. But when you go back in the literature, you also find that we have a few recent studies on oceanography in the James Bay. So what Niskamon is doing with University of Quebec at Rimouski is to try to understand what is happening there. So the project includes many aspects of the oceanography. So, but in this presentation, we focus on salinities due to the place that the role of the salinity in the structuration of the aquatic communities. So is the objective or the purpose is to provide so that we help to manage or adapt future projects or management projects with population there. So what I'll present today will be on my objective to analyze like the dynamics of the salinity along the SN course of James Bay. To do that, what I'll present firstly will be like the spatial temporal variability of the salinity to show you what is happening there when you're moving to one season to another. But also I'll make a point on these forces to try to quantify them and show with you how that forces affect the variation of the salinity from one season to another or depending to another parameters. So to do that, we moved there and we installed the mooring from different seasons and we did CTD cast. So we obtained data from the currents, water level, salinities, But for this presentation, we also take the data from ERA 5 reanalysis, especially data winds data. But we also obtain, we thank the team from University of Quebec at Montreal, who provide us data from river discharge there, especially around La Grande Rivière. So what can we see when we try to understand the seasonal variation from one season to another of salinities? So the first thing that you can obviously see is the difference between winter and summer can be like not very obvious, because when you see, we are supposed to see the opposite situation, but here you will see that the freshwater depth is more depth than the freshwater depth in summer, contrary to winter. This exactly is due to the construction of the hydroelectric complex, because here in Quebec, to provide electricity, we need in summer, because in summer we need like electricity to run. So the production of the energy around La Grande Rivière is very important. So it will reduce the salinity in winter, and the depth of the freshwater layer is something around, we measure it as something like 5 or 6 meters. This is relatively different when you move to summer, where that freshwater depth is relatively near to the surface. So we did that with some CTD casts. We have many of them, but we take these 3 just to show what is happening there. So, and after that, we try now to understand how that forces are affecting the variation of salinity. So let's start, for example, with the current. So as I told, we installed 2 ADCP, one near to Eastman. Eastman is another river that were deviated to provide water in La Grande Rivière. And another ADCP that we installed at the last summer. So I will show you what we can see around La Grande Rivière the last summer. So here is the variation of the current. And you can see the direction of the propagation of the current, depending if you are near to the surface or if you are near to the bottom, depending on how you are seeing it. But something that is very interesting is to see the variation of the intensity of the current with depth. This is very important, because after that we try now to understand how that variation of the current, depending from the from surface to the bottom, will change the variation of salinity. On the other hand, we also install like the mooring of CTD mooring that will help us to have time series of salinities at different depths. So if I took, for example, at near to the surface, so something around 1 meters, I have a mooring there that I have the salinities data, but in other hands, I also have at a certain bins the currents. But what we will do here first, before we correlate it, is we did like the principal component analysis to define the main component, the dominant current, to link it with the variation of the salinity. So for example, as you can see here, this is the wavelength analysis that we operate to compare or to see the correlation or the effect of the currents, surface currents with salinity at different scales. So here you can see the scale, and here you can see the days. So when we compare these 2 parameters, we see that there is a low correlation between the surface salinity and surface current. It's so that at some days you can see important current and with different phases, like positive phases or negative phases here. And what we can also mention there is that that correlation is also significant, because we test it like at 95%. So we also try to see if we move around 5 meters, what is happening is that now we have more correlation between what is happening with between current and salinities. Here we have the correlation between the salinities and the current at 5 meters at the scale of moving between 0.5 to 4 days, as you can see here. So when you're moving with the depth, you will see that the current really affects now the variation of the salinity around that point. So we tried the same thing to see what is happening now when we compare the winds, the surface wind that we obtained from reanalysis from ERA with the salinities. At the same time, we see that the correlation is relatively low, but it's also important with positive phases, especially. the scale of correlation vary from one day to another. That can also be explained by other meteorological parameters. So as you can see here. At the same thing, like with the previous case, we have the data of the winds. We focus on the dominant winds, so we obtain it by looking for the we do the principal component analysis. We take the vector, the main vector, and we compare it with sanities. So what can we say now with sorry for this? What can we say now with river plume around La Grande Rivière? What is happening when the river distance increase with the salinities? What is good is that at the previous year, some scientists established the correlation between the river distance and the length or the surface of the plume of La Grande Rivière. And for do this, you are supposed to take some consideration. That consideration implies like the isoalane that you consider of the salinity, because it will be different if you consider 5 PSU, 10 PSU, or 25 PSU due to the stratification or the zonation of your river plume. So when we do that by using this relation that Messier established some years ago, we can see with me how the river plume vary with the river discharge. Here is in winter. And to do that, we also have to consider, another consideration is that all the water is covered by ice. So we verify that configuration to do that relationship. And what we show you here is what is happening for the period of our measurement. So it's like the mean of the propagation of the length, of the mean of the length of the river plume. As you can see, it's something around 61 or 62 kilometers. So the take-home message for this part, because this is the part of the global, as I say, of the global project that we are studying, and other parameters also. But at this point, the take-home message firstly is to remind what is happening in La Grande Rivière around James Bay, with the increase of the river discharge. You will see that the first point is to remind that the depth, the freshwater depth is very different from 5 meters in winter to around 1 meter in summer. Another thing to mention is the stratification that is very stronger in winter due to the suppression of winds, or due to the suppression of the effect of the wind with the suppression of the ice at winters. Another thing to mention is also the fact that we have the significant and regional internal variety of salinities. The effect of the current is very different when you consider it at different depths. But what we'll show here, maybe in the next month or another presentation, is to mention the fact that that relation needs to be understood very well. The relation between the salinity and that forcing. As I previously said, when you see, for example, the correlation between the wind and the salinity, you see that there is another parameter that is applied to modify the impacts of the wind in salinity depending on scale, because you have something, the correlation at different scale. So there are another parameters to understand. So we need to most study these parameters to understand how they work, how that forcing really acts on the variation of the salinity this last year. So at the end, I want to thank my field team leaders, but also thank the CRIS communities, because they help us and they were with us in the field with the boards. Yeah, thank you very much.
Thanks, Manfred. That was really nice. We're kind of running a bit late, but do we have a question for Manfred? So maybe I have a really quick one, but it's more a comment. I mean that was really nice. The wavelet correlation really seemed to do, or sorry, the wavelet coherence seemed to do a really good job for you, right?
Yeah.
Kind of an underutilized tool. I guess maybe more people should pick it up. So I'm glad it worked so well. Okay, so I got the wrong screen up. Who do we got next? So our next speaker is Jackie Chen. So you can grab screen.
Okay, I'll just show my poster.
Yeah, so you got it's a quick description of your poster, if you will, to add.
Yeah,
Come tomorrow.
I'll keep it quick. So, hi everyone, my name is Jackie Chen, and you can call me Jackie. I'm a PhD student in York University, and my professor, Peter Taylor, has given a talk in the last section. Our team has been studying marine fog, and the location we are interested in is the Sable Islands. On the map is here, it's very small. And there are a lot of fog in this area. People think that it's a good place to study marine weather because with the land, you can have your instruments there, and the land is so small that it is not going to impact the observation. Environment Canada has weather stations on the island too, and when we look at the reports, we found that there's a diurnal cycles of the temperature as well as the fog. So, and the two matches. So basically, when it's hot in the daytime, there are less fog, and it's cold in the nighttime, there are more fog. So we use the WRF model to do a simulations on that. We use two different settings of domains. One, we only have two domains. This one is cursor, but can cover the areas that we are interested in. But in these settings, we don't see the land, and the model won't give you the land at that grid point because the land is too small. But we can manually set that grid point to be a land. And the second settings is to use 4 domains and really zoom into the island there. And in that resolutions, you can see the islands. So with 2 domains, we do the simulation for 3 months in the summers, for water surface or for land surface. We found that with water surface, we got more fogs. So there are more heating, but there are also more false alarms. So it reports the incorrectly. And with land, there are less fog in total. So less false alarm, but also less heat and more misses. So it missed the real fog. And for 4 domains, you can see the details of what's going on in the surrounding area. So can see the land have a higher temperature and lower liquid water, and the wind is coming from the southeast directions, so it makes the downwind area hotter and makes it less liquid waters. So either in the model or in the observations, we found that the land can have some impacts on the results or on the observations you have. So we want to argue that we have to take this into considerations if you want to have some measurements on the Sable Islands, especially the Fatima campaign coming next month. And for the model, for the WRF models, we found that with the land, it can have a pretty good temperature predictions, but the liquid water prediction is not good. It has too much liquid waters, and the time periods is not correct. So this is the directions we are looking into. And basically that's it. Thank you.
Thanks. I apologize for the telemarketers calling my house in the middle of that. Do we have questions, or should we have a little bit of time, so we can't have questions now, but we can also save them for the poster session. But,
yeah, but the post discuss session is tomorrow, so if you have questions, right, you can ask.
You can think about it overnight. You can give them homework if you want.
Okay.
Okay, doesn't look like anyone's got anything in the chat, so thank you so much for your talk.
Thank you.
So let's have a look. So the next speaker is Rebecca Boitel, which I'm almost certainly mispronouncing. So Rebecca, you can grab your screen and maybe give people a minute to come in.
For sure. I will share it.
I hope my
And-
PhD students here, given what you're talking about, but yeah, I don't know.
Yeah, you pronounced it the non-anglicized version of the name, so you're probably more correct than how I pronounce it anyways.
Okay, my wife's Francophone, so I've been trained. So anyway,
Should I go ahead?
yeah, you may as well just get going.
All right. Thanks everyone for coming. Today I'm going to be talking about the work that I've done with Susan Allen at UBC on the Lagrangian analysis of seasonal and interannual trends in the estuarine flow, composition, and path within the Juan de Fuca Strait. And you can see the Juan de Fuca Strait in this beautiful aerial image right here. And then this is the rest of the Salish Sea. Oh, I have to use my notes. So today I'm going to be going briefly through some motivation for the project, important background information to understanding what I've done, and then the preliminary results that I have so far that I'm confident in. The results that I'm going through today are primarily Salish Sea focused and not too much on the shelf yet, but that's where I'm going into later. So first off, why do we care? For those who aren't familiar with the Salish Sea, it's a semi-enclosed estuarine sea between BC mainland and Washington mainland and Vancouver Island. It supports an immense population on the coast. It's home to one of the largest ports in Canada and many critical ecosystems, many of which have seen a decline in populations in recent years that have been directly linked to biogeochemical changes in the region. But accurate modeling of these biogeochemical changes is really challenging in this area because it's orders of magnitude more variable than the nearby open ocean, extremely physiographically complex. And because it's such a small region, its modeling accuracy is incredibly dependent on the accuracy of what we know about the boundary conditions. And the main boundary is this opening at the Juan de Fuca Strait. It's essentially closed here at Johnson Strait. Before I leave this slide, I do just want to draw your attention to the red line showing the foul leg of the region, and also this orange cross section that I've drawn. It'll make the next slide make a lot more sense. So here's the foul leg plot of the flow. As I said before, it's an estuarine sea, so water comes in deep through the Juan de Fuca Strait. About 30% of it is advected back to the surface, either through the top to bottom mixing in Harrow Strait or while it's in the Juan de Fuca and leaves back through the surface outflow of Juan de Fuca Strait. About 56% makes it to the Strait of Georgia, which is the large basin on the Canadian side of the border, and about 14% makes it to Puget Sound, which is on the American side of the border. Here I'm showing the general flow path from Ianson et al. Within the Juan de Fuca Strait to the Strait of Georgia. It is an estuarine system, so most of the time we see this fast outflow at the surface and slower inflow at depth. Because it's rotationally modified, we get this pooling of water on the Canadian side of the coast and more so during neap tides during spring. But this estuarine flow doesn't hold true all the time. In wind events, about 55 or about 45% of the time in the winter and only about 10% in the summer, we get a reversal, or what's called a reversal in the flow, but it's actually more of a vertical shift. So we have a lot more horizontal variation in the flow regime rather than vertical like we had in the estuarine regime. The types of transient regimes aren't too well defined, but can be separated into a surface flow generated regime or an intermediate flow generated regime. And this is from Thompson et al. These are adapted from Thompson et al. In 2007. I'm doing this work from a water mass perspective rather than currents perspective on the coast, so we can really talk about how the composition of water is changing and what we're seeing today instead of talking about the currents. The important water masses that I'm looking at are the Pacific equatorial water, the Pacific subarctic upper water, and the Eastern North Pacific central water. Here we have estimations from Thompson and Krasovsky 2010 that show around our region the water coming in from the California undercurrent, which is one of the major currents in that area. It will be about 30% Pacific subarctic or Pacific equatorial water and 70% Pacific subarctic water. The other important sources to look at are just the advected stuff from the Juan de Fuca outflow, and then also stuff coming up from the Columbia River during transient flow. Previous work in this area in the region has really focused on the summer conditions or has treated all Pacific water masses as one oceanic water mass coming into the Salish Sea. So this work hopes to bridge the gap between those previous studies. To do this, I'm looking at outputs from two different models. My group's Salish CCAS, which is a high resolution 3D circulation model with coupled biological and carbonate chemistry models within the Salish Sea, which is fun because in that way, we don't only look at the salinity and temperature tracers, but can also look at a lot of fun biological and carbonate tracers. And then the other model that I'm looking at in order to get the shelf flow information is a model that from the DFO, the Canadian Ice Ocean Prediction System West Coast model, which is lower in resolution, but has the shelf flow characteristics and as well as temperature and salinity information. The output from these models is being analyzed using Ariane, which is an offline Lagrangian simulator with two modes. I'm primarily using the quantitative mode for my analysis, but also using the qualitative mode as an exploratory step to figure out very good boundaries. The quantitative mode isn't the most intuitive thing to think about, so I'm going to delve into it a little bit here, but basically you come up with one initialization boundary where all your particles that you're looking at or water parcels that you're looking at start at, and then you're tracking their flow. Forgive my PowerPoint drawings. And then you're tracking the flow to boundaries that you've set. Here I've set boundaries for each of the channels going into the Strait of Georgia, and then for each of the channels going into Puget Sound. So you don't get any information about the stuff that gets lost within here, only the particles that actually end up reaching a boundary or crossing back over the initialization boundary. I've done a bunch, this figure is from my analysis within Salish CCAS. For PSYOPS West, I've done similar analysis within Salish CCAS, trying to get the boundaries to match as closely to the Salish CCAS boundaries. And then I'm also focusing using PSYOPS on the shelf. These are boundaries I've set to look at the flow within the Juan de Fuca eddy. And then these are for more offshore flows to see where the water masses are coming in and from which direction the flows are coming from. Now getting into the results of this analysis, shown here is a cross-section of the Juan de Fuca Strait, the same orange one I showed beforehand, with water parcels originating in the Juan de Fuca Strait that eventually reach one of my boundaries, either going to Strait of Georgia or to Puget Sound highlighted. In the summer, you can really see the estuarine regime happening here, this strong pooling on the Canadian side of the shore, and then the inflow focus at this intermediate depth here. In the winter, it's a bit more complicated because we have both the estuarine and the transient regime happening about half the time. So you can see some characteristics of the summer estuarine regime here, but then also a scattering of water coming in from different depths in different areas within the strait, suggesting that both the intermediate and surface generated estuarine regime are at play here, not one or the other, as well as the estuarine regime. This variability, or the impact of this variability on the flow paths in the winter, is visible in the analysis if we look at the water product properties. Here we have hydrographs for the water properties of water, again, starting in the Juan de Fuca Strait and getting to one of those other channels in all of the years that I looked at. I'm only showing plots or hydrographs for dissolved silica here, but that's because for all the tracers, they do look quite similar or tell a similar story. In the summer, we see, due to the upwelling events that occur in this area in the summer, really, really high concentrations in all of the tracers. And this is consistent year to year. Whereas in the winter, whether or not they're high concentration, low, or just variables in somewhere in therein, doesn't really have a distinct pattern. And it changes a lot year to year. If we compare the water parcel tracer concentrations to ambient tracer concentrations in the Strait of Georgia and Puget Sound gotten from climatology, we can see whether the inflow is increasing or decreasing, increasing being in red and decreasing being in blue, the tracer concentrations in the sea. Unsurprisingly, the summer concentrations during upwelling are all increasing the concentrations in the area, but we see a mix of the two in the winter. I've only shown this column is all carbon, this carbon is all nitrate. Both dissolved silica and nitrate were very, very similar in their distribution, not necessarily concentration, and both carbon and salinity were very, very similar in how these plots looked. So yeah, drawing your attention again to the winter, we have a variability at the surface and at depth, but also variability between tracers. So consistently dissolved inorganic carbon and the salinity are brought in at the surface, or are lower in concentration at the surface and higher in concentration at depth, which makes sense. But interestingly, we have this intermediate pocket of lower concentration nutrients, a surface pocket of very low concentration nutrients, and then at depth, higher concentration nutrients, which again can be connected back to the surface versus intermediate types of transient flow regimes within the Juan de Fuca Strait that we see in the winter. Here we have the expected shell flow path that would be responsible for this variability within and between the summer and winter. I've shown here the dashed lines are for paths that are of deeper flow, and the solid are more shallow inflows. So again, the surface versus intermediate flow that we see coming in with very different water properties is something that's going to be really interesting to see whether some of these paths can explain those differences in properties we saw in the previous cross sections. Here I have a little teaser of what the particles actually look like in the qualitative flow, but unfortunately we did find a bug this week in one of my runs, so I'm a little suspicious of the results that I have right now in my qualitative and quantitative flow. Unfortunate timing, but hopefully by the end of the week or early next week, I'll have those runs redone and have more shareable results. So please reach out if you're interested. Even with this bug though, there's a lot of interesting results that we can come to, or conclusions we can come to based on the deep level of analysis done within the Salish Sea. Primarily just the fact that the driver of a lot of the variability we see in the conditions within the Salish Sea can be explained in the winter, and winter hasn't been looked into enough in this region and is worth looking into more. Summer conditions, as I said, are similar year to year, while winter varies significantly, as well as winter varies with depth and tracer type, whether it's going to be an increase or decrease in concentration. So as such, when I do finish a bug-free version of my runs on the shelf, we expect a large variability in shelf path and thus water mass source into the Juan de Fuca inflow. Thank you so much for listening.
Thank you very much. Do we have questions for Rebecca? So people are not putting a lot of things into the chat. Well, I guess, okay, well, I'll ask. I love bugs. What was the bug?
Oh, so yeah, it feels like we're recording it right now. The problem is that I'm putting sea surface height into my qualitative runs. So I have information from SciHouse, which is both the U and V direction, that I have to convert to including the tides. So I don't have my surface, my vertical flow. I'm artificially creating these tides with the baroclinic hourly and the barotropic daily. So doing these runs with sea surface height included, but not including the vertical velocity, I've never done and no one in my group has done before. So I had it in and it was working for most of my flows, and I got really, really confident with it working in one folder. And then I tried to run for a different month and there's a pointer error, and pointer errors kind of lead us to believe that the runs that were working, it was because the simulator was not finding stuff sometimes and then finding something and putting it in and it working. But because there was a pointer error in a different run, the stuff it was finding probably wasn't the right stuff. So although I had been very pleasantly tricked into thinking my runs were working, they were unfortunately not.
Well, you caught it now, so that's good.
Yeah, we caught it. So
I won't be mistrustful of your data,
I'm
right?
very happy, although it was bittersweet to find it this week and not have anything to show. I'm very pleased that I did not show stuff with a pointer error and have everyone tell me, please don't go that way. So better this way than the other.
Okay, excellent. So Shumin has a question. You can unmute yourself and ask if you.
Oh, thank you. Hi, Becca. That was a really good talk. I really enjoyed it. I just think I probably missed something in one of your figures. As I recall, there's a kind of a yellowish the color, and I see the unit on the
Do you remember which figure?
it was a gram per kilogram. I was just can't help wondering. I think
These ones?
yeah, this one. What is the
Yeah, so this is the flux through each grid cell of water parcels. So it's not the most intuitive. Yeah, and then the flux through each grid cell of the water going multiplied by the units of that tracer. So these aren't just flux figures, these are also multiplied by the carbon tracer units. But for the purposes of flux dominates the flow, no matter which tracer I multiply it by, these look very much the same. But yeah, I should have specified that this is the flux multiplied by the dissolved inorganic carbon coming in.
Oh, that makes sense. Thank you. Yeah.
Okay, excellent. So why don't we move forward then? Thank you again, Becca.
Thank you.
So the second last talk of the session is Ajay Ravindran. Are you here, Ajay? Or Ajaya, sorry. Okay. I am looking around and I'm not finding. Well, so I guess got a couple of choices. I guess, Adam, what do you think?
But we could open up the 15 minutes to questions for previous speakers.
Yeah, seems fair enough. Guess we could do that. Does anybody have questions for? We were not overloaded with questions. That's is the problem, right? So. It's the
I think
peril.
Susan has her hand up.
How do you see that? Oh, here we go. Susan just, yeah, it's tiny type. Susan, go ahead.
I just wanted to say hello to everybody across the country. It's just really nice because nobody's got a question. Just really nice to see so many people here. It's great to see 40 people in the room, and we've got people from right across the country. Appreciate all of you back east staying up late. Don't expect too much from me early Friday morning. But yeah, just hi everybody.
Well, it's good to see you too. Rachel has a question in the chat. Rachel, do you want to just ask it? I mean,
it's a bit loud here with crying children, but I was wondering about the recommendations for the Fatima study.
Well,
that's for you, Jackie. Yeah.
Yeah. Well, for the recommendations, well, yeah, we don't have instruments for the Fatima program because we cannot get the fundings, and I think we need to look at the wind there and try to have the that is in the upwind directions, and that will mostly minimize the impacts of the land. And yeah, and we all can. I think that we also have the shipment or the measurement on the ship, and we can also compare that and see how large is the impacts of the land, and we can do an adjustment on the observations. Yeah.
Perhaps I can put a word or two in there as well. What we were hoping to do was to put up a relatively tall mast towards one of the ends of the island so that it would be relatively unaffected by the land. I thought we had a chance under the NSERC Alliance international program, but we got caught by one of their catch-22s in terms of dates. So we didn't get any funding for that. There are people who are going to be flying UAVs, and they could get some profiles of the variation in the liquid water content, the visibility with height above the ocean. But I guess one of the main things that Jakey and the group at York have been doing is to argue that there will be deposition of water droplets to the water surface, and that should in fact reduce the liquid water content as you come down towards the surface, which WRF and other models don't include in their standard operation. So profiles was one of the things we're particularly looking into, and I tried to persuade the Fatima group to move some of their measurement stations closer to the water's edge, but they seem pretty set on what they'd planned to do.
Okay. Paul Myers has a question.
Sure, I have a question for Amina. Thanks, nice presentation. And as you know, I'm always interested in anything Labrador Sea related. So, related to that, over recent years, people have been looked at and seeing sometimes the location of convection has been shifting a bit more to south of Greenland, and even in some years in the Erminger Sea. So have you thought about sort of, looking at representative profiles for different regions, different years, and understanding what strength of air-sea fluxes are needed to drive deep mixing? And also related to that, when you look at the air-sea fluxes, how much of the deep mixing is just driven by strong winter cooling versus events of very strong cooling when storms come by?
Okay, that's a really good question. So I have been doing a little bit of digging into that, not shown in my presentation. I've been looking at the maximum mixed layer depth achieved given various NAO, like mean NAO years. And so what we find is that even though like some years can have a very similar mean NAO index, even close to zero, so like nothing really remarkable about that, they can have really different mixed layers. And so my limited, like I've only really started to scratch the surface on that one, so I don't have a great answer for you just yet, but it's in the works. What we've noticed is that the timing of those cold air outbreaks is really important. So a lot of those extreme events tend to get washed out in the mean. But when they happen closer to the late January, early February kind of time region, you can get a much deeper mixed layer after the stratification has been weakened. Whereas if those events happen earlier in the season, then they tend to have less of an effect on deep convection. So I think that answers one of your questions. And the other one was regarding looking at other regions of convection. Yeah, so in short, I have not looked at other regions, though I do plan to kind of validate what I've been looking at in the Labrador Sea with convection in the Erminger Sea. I know some work has been done on that previously. So again, that's just a future step that I haven't gotten to just yet, but thank you. Does that answer all of your questions, or did I miss something?
No, that was great. Thank you very much.
Okay, how are we doing? Did anyone else out there have anything?
I think there's two in the chat now, Merrick.
Oh, is there? Okay, sorry, we gotta scroll to the right. I was looking for the hands up. Okay, so what do we got? So Rachel was the last one. So Fred Dupont, do you want to ask your question?
Thanks, Marek. Actually, my phone is just ringing now, so I'll pass and
Okay, well, mute yourself and I'll read it out for you. That's fine. I know all about phones ringing at the wrong time. Okay, so this is for Romina again. Have you tried other climate indices like AO instead of NAO?
So the short answer is I have not. It might be interesting looking into that in the future. So thank you for that idea. I'm not entirely confident that will have a huge effect, but I don't know, worth looking into, especially just with their findings that the Icelandic low index is kind of the strongest modulating factor there. I think larger indices like that might be comparable to the NAO, if not less. That's just my idea, but yeah, definitely worth looking into. Thank you.
Okay, thanks. Yu Lu actually has a question as well for you, Romina. So Yu, do you want to ask yours, or is your phone ringing too?
No, it's not me. So especially look at the Icelandic low NAO and the QNet, surface net. I would think they are kind of correlated, right? So and just kind of if they are correlated, why do you what's the value to separate them?
Yeah, so they definitely are related. And somewhere also not shown, I have a plot, which I wish I had on hand for you, that just highlights their correlation. And so I want to say it's only about, the NAO only explains about 60% of, if I remember that number correctly, of the heat flux variability in the Labrador Sea. So while they are correlated, they're ultimately, not the same thing. And so I think what's often forgotten is that, like with the NAO, right, you can have a strong positive NAO if you have like a mediocre Icelandic low and a really strong Azores high. And so the Azores high is, really distant from the Labrador Sea. And so even though the NAO can be strongly positive, it doesn't necessarily mean that there's going to be strong heat fluxes in the Labrador Sea. So they are correlated. There's no denying that. I just, there's more to it than that. Does that answer your question?
Yeah, I think QNet is a fundamental. So everything, what's drive convection is a surface net heat flux, right? So the other thing is just an index, indices. Okay.
Okay, I think that's everybody in the chat. So I'll grab a question in that case. It's more sort of for the group, or maybe even for Paul Myers and other people who do the modeling. So Manfred showed really neat things in James Bay, and I'm wondering whether these new high resolution Arctic simulations have those river outflows that Manfred showed data for.
Is that a question you want me to answer?
Well, I think Manfred, to be fair to Manfred, I think he's a field guy, so I'm not really sure he wants to answer model questions. You might be the guy who knows best.
That's a really good question. There was recently an NSERC CRD project, collaborative research one, linked with Manitoba Hydro and Quebec Hydro, where actually they were a hydrologist. There's a CRC chair in Calgary, Trish Stadnick, who's actually took various reanalysis and climate simulations, use it to force a hydrological model to get the runoff for each of the different rivers around Hudson Bay, James Bay, and the Arctic. And it makes a huge difference in terms of what are some of the impacts, not on James Bay, but on the Arctic. There's a talk by one of my students, Taya Weiss-Gibbons, next week in the CMOS section, who's going to specifically be looking at what is the sensitivity of the models to river products. And it's significant. And I'm assuming Susan can probably also comment a lot, given all the work, the importance of rivers in the Salish Sea, for example.
So I recently moved from climatology for a bunch of the rivers to actually trying to use daily rivers from the measurements we have. And yes, it makes a significant difference. We always had daily Fraser, which is the dominant river, but particularly in Puget Sound, where the rivers are really important in the winter as well, big differences.
Right. Okay. Well, I thought that was a really great discussion. We've already had one person ask me whether all the talks are done. So I think in the interest of satisfying the people who came to see our final speaker, I'm going to pass the floor to Paul Kushner, and Paul, take us to dinner. Oh, wait, no, wait, sorry. There's a question from Helen Joseph. Let me just read that out before I hand over the roll. So Helen asks, not a scientific question, but I was wondering how you as researcher students have managed during the pandemic. Has the lack of being able to get together for this Congress or other information sessions, I guess, affected you? There's a missing expression. So, I mean, yeah, I don't know. I mean, it has kind of dragged on, right?
Sure. Definitely affected us in lots
so, I mean,
of...
I have to say, I went to EGU last week, and it was kind of wild in the sense that it was hybrid. So a lot of stuff was broken. But there was just such an appetite, especially in the younger European researchers, to be there. I kind of felt like I didn't know anyone anymore, because I think that the attendance might have been sparser on my end of the age spectrum, and the young people were out in force. So I think we're back. At least I hope we're back. But I mean, the upside is, a lot of people can make time for virtual sessions. So I mean, I guess I would encourage the community to, learn from what we had to face, and maybe kind of make it better for people with kids or sort of home situations that don't allow them to travel. Helen, did you want to add something before we give the floor to Paul?
No, that's fine. Thanks, Mark. I was just thinking and enjoying getting together in a virtual manner, but then looking forward to the face-to-face meeting next year. And I wonder if it's had an impact in terms of, networking or finding out what other researchers are doing, if it's kind of stalled anything, or people have just found a workaround, basically.
I mean, I guess I would probably say that's a very individual, kind of dependent on individual situations, but yeah. Okay.
Thanks, then.
Thanks, Helen. Let's throw the floor over to Paul. Sorry, Paul, I didn't mean to.
No, not at all. It was nice to have that question. So hello, everyone. I guess I'm keeping you from dinner, right? So I will try to keep to time. This is definitely a work in progress. The conclusions change every time a new simulation gets done. I haven't shared my screen yet. Yes, sir. This is definitely a work in progress. It's really the analysis has mostly been done by Stephanie Hay, who's a postdoc at the University of Exeter, formerly at U of T, Alexandre Odette, who's in my group now, and James Green at Exeter is also helping out with this analysis. So what we're trying to do here is use simulations in which we take Earth system models, coupled ocean atmosphere models, and force them separately with the effects of greenhouse gases, keeping sea ice fixed, and driving sea ice loss, as we see under greenhouse warming, and keeping the greenhouse gases fixed. And so to motivate this, we are this idea that we can run these expensive models for a very long time and do these kind of idealized experiments. There's a lot of literature on this. We've been involved in this. It's getting to be over a half decade now. Basically what we do we run these simulations with kind of these separate forcings, treating sea ice as a forcing instead of a part of the Earth system that it freely responds to greenhouse gases, because there's a lot of interest in understanding the polar amplification of climate using kind of idealized experiments like this and intervening in the physics. So what's driving this actually is the fact that a lot of Earth system models disagree on the degree of Arctic amplification per level of warming. And there are demonstrable issues with the amount of sea ice loss that models exhibit in response to greenhouse forcing. So these various motivations drive this kind of a set of idealized experiments. And I'll mention at the end of the talk a project called PAMIP. Actually, I'll mention it in a couple of slides, which is seeking to kind of coordinate these experiments. So that's also driving our interest here. So I'm going to go back to a study that motivated this kind of ongoing work. This was Kelly McCusker, who looked at the Canadian Earth System model, CanESM, and its response to sea ice loss, which is SIL here, greenhouse gas forcing, so doubling of CO2. And this is the response in surface air temperature, all right? And what you see when you impose sea ice loss and keep the greenhouse gases fixed in this coupled ocean atmosphere model is lots of Arctic warming, which isn't surprising, warming that extends into lower latitudes. And then if you look at the response of the circulation, you can see that that mid-latitude response is also present in affecting large-scale circulation features, so a deepening of the Aleutian low, for example. But you can also play a game of keeping sea ice fixed or constrained as much as possible through nudging, and you increase greenhouse gases, and you see actually a pattern of warming. Now, it shouldn't be too surprising that there's warming in response to greenhouse gases, but that warming is still present in this model in the Arctic, even when sea ice is held fixed. And we see also a sea level pressure response. Now, what we were just interested in a basic question: if we add up these two responses, and we get this sum here. So this is just the simple sum of the two patterns here on the upper left and the second column here. And if you look at a simulation in which both forcings are applied together, so these are simulations run about 200 years, where both sea ice loss from the first experiment and greenhouse gas carbon dioxide doubling is applied, you get a very, very similar pattern, and you can do a pattern correlation and find that the square of their correlation coefficient is 98%. So, okay, so this is a very well explained and a very, I would say, a very linear response, or very additive response. And if you look at sea level pressure, you can kind of see that the numbers, there's sea level pressure is a bit noisier, but you can see that you're up at 90% or so. What's interesting is that you can even look on regional scales. So we can take this surface air temperature response and decompose it into high pass and low pass spatial scales. So this is synoptic scales, so wave number 5 and lower. And you can actually track individual features of the response. So for example, the Hudson Bay warming here, right, shows up strongly in the sum, and it's also here in the sea ice loss. So we can actually attribute different features of this response to one forcing or the other, and still get pretty good additivity even on small scales. So motivated by this, we thought let's kind of broaden this and look at other variables and other models. And so we thought a little bit about, well, what are we really after here? So first of all, additivity is just a basic test. If responses in separate studies of any kind can't be added up, right, then it's a lot harder to do attribution. So if the responses are linearly additive, then we can attribute a response to sea ice loss or greenhouse gases in isolation. The second test we want to apply is that, if they're additive, are the responses separable? And I'll show you an example of separability and non-separability even on the previous slide. So for example, we can see that there's a lot more Arctic amplification with sea ice loss than with greenhouse warming. So we would say that, in this pattern, there's a part that's much more attributable to sea ice loss than greenhouse warming in isolation within these experiments. But you can see here this deepening of the Aleutian low shows up in both experiments. So that's a response that's hard to attribute, even though it adds up fairly nicely. It would be hard to attribute a deepening of an Aleutian low to something that is attributable to sea ice loss in isolation or to the rest of the global warming process in isolation. So that's separability, and one way to measure separability is to look at this the spatial correlation, and if it's low for a response that's additive, then we could say that the patterns are spatially independent, and we can attribute the response to one or the other forcing. And finally, robustness is a measure that we apply across models and model experiments. If we see similar patterns of response in these experiments across different models, then we have some confidence in these predictions. All right. Now, we actually haven't done this analysis, and I think it'll become clear why we haven't really gone into quantifying robustness and to a great degree. But basically, what you'd look at is the spatial similarity of responses across different models and experiments. So that's the basic idea. And what we're doing is looking at three set experiments so far. So these are very expensive simulations. I found we've learned a lot just by looking at these three. So the first two are one I've mentioned before, the study from McCusker et al. With Kenny SM. And what's done in these experiments is you induce sea ice loss. So you go from a state of high, this is for this Kenny SM, high sea ice, high Arctic sea ice to low Arctic sea ice, just by using some basic nudging technique. All right, and you keep greenhouse gases fixed. That leads to a little bit of warming in low latitudes. So you can see there's a bit of warming, but not very much. All right, and you can also double CO2 and try to constrain sea ice. And when you do that, you get quite a bit of warming at low latitudes and a little bit of sea ice loss because the nudging method is imperfect. All right, and then you can do both at the same time. And this was done with a couple of models with the CNRM model in a study by Thomas Udar and others, now getting to be 6 or 7 years ago. We've also looked more recently at experiments just completed by Alexandre, and these follow a different protocol. So we're doing the same thing with a doubled CO2, but we're nudging towards different sea ice targets according to this model into comparison project called PAMIP, Polar Amplification Model into Comparison Project, where Arctic sea ice and Antarctic sea ice are prescribed separately. All right, and it turns out there is a difference between these methods because the sea ice forcing used in these recent experiments is actually a bit weaker than what's found under doubled CO2 conditions. All right. So let me just kind of walk you through some of the diagnostics that we do. So we have a couple of models, all right, and I'll just start with the basic measures of additivity and separability. All right, so this is in the upper row here is shown the temperature response to sea ice loss, greenhouse gases, their sum, and sea ice loss and greenhouse gases imposed together. This is for Kenny SM2 under doubled CO2. And the bottom row shows the winds, all right, and on the right 8 panels are all from the CNRM model, all right, and then the statistics here are the additivity, all right, this 100%, so very, very good agreement between the two simulations. This is the zonal mean temperature, the zonal mean winds, and the separability relates to the pattern correlation. So if the pattern correlation is quite high, as it turns out to be here, it's about 0.6, 0.57, that sort of falls below the threshold where we really find the patterns are easily separable. And 0.26 it suggests that the patterns are actually anti-correlated or are weakly correlated. All right, so what we see here is that for temperatures and winds, we have good additivity. You can see, very high numbers bolded here, all right, greater than 95%. And separability, that's kind of model dependent. So it turns out in the French model, there's a bit of cooling in response to CO2 doubling when sea ice is held fixed for rather mysterious reasons that we're still trying to understand. This is not actually a significant cooling, but it shows up as a really strong minimum and warming at the very least. And as a result, the sea ice loss and greenhouse gas responses in this model are actually more separable than they are in Kenny SM2. In the winds, we consistently see that there are very different responses to sea ice loss and greenhouse gases. Often these effects oppose one another, so there's actually a weak anti-correlation. And so we would say that additivity and separability and robustness, you can see lots of similarities between these patterns, holds to a good degree in these simulations. So we can look in more detail, and part of Steph's thesis work was to really understand the surface energy budget and the surface ocean response. And when we look at, for example, the sensible heat flux in the ocean in response to sea ice loss, there's increased heat flux out of the ocean, all right, in the Arctic particularly, but there's a real pattern of change that is quite different in the Atlantic Ocean, for example. And we can see that additivity, perhaps not surprisingly, and since it's so coupled to the ocean processes, holds a bit less well than for the large scale circulation, all right? But we see additivity on the order of 75% or larger for both the surface evaporation and CNRM and sensible heat flux. But the evaporative response, you can see some real nonlinear features that are showing up here when sea ice loss and greenhouse gases are imposed together, all right? So, and another thing is if you start to scan the patterns, you do see that the responses are not really robust across these models for these surface energy budget features. So what we've done is kind of extend this to lots and lots of variables. So what we're trying to do is create kind of a portrait of what's going on. So let me talk, and I don't know how my time is here, but I'll just say that we can classify responses as being additive and separable, both satisfying both things. So we would have a top square in these sort of paired rows that is dark, and a bottom square that's dark. If they're additive but aren't separable, so we can't really separate those patterns of response, then the lower square would be in a lighter shading. And if they're neither additive nor separable, so if there's real nonlinearity going on, we get this kind of light shading. All right. So for example, for the surface energy budget response I showed you, the different colors indicate the degree of correlation and so on. But really what we're saying here is in the seasonal cycle, January through December, for sensible heat, latent heat, shortwave, and long wave. Sorry, the colors don't indicate correlations. Actually, the intensity of the colors indicate the strength of the correlation. We see that basically for the surface energy budget, we have reasonable agreement, but it starts to break down when we look at certain certain features. And this is for the Northern Hemisphere as a whole. When we start to break things down even further, and this is a plot showing just an example of the kind of diagnostics we're doing, sea surface temperature, salinity, the barotropic stream function in the ocean regions we're considering, and its pattern, and the maximum mixed layer depth to measure convective depth. For CANI-SM2 on the left and CNRM on the right. All right. What we're seeing here is that specifically if we get down to the Atlantic and compare it to the Pacific response, that CANI-SM2 has a lot of nonlinear responses. And we actually saw this earlier on, and we're looking for ways to quantify this behavior and really pull out which seasons it's strongest. So we can see that in particular for sea surface salinity. I mentioned non-robust evaporative responses. The polar gyres, the mixed layer depth, convective depth in the ocean. There's a lot of signals that are simply not attributable to sea ice loss or greenhouse gases in isolation. We have to sort of consider them together. And the separability is interesting too, because what we're seeing is that in a lot of cases for the ocean responses, particularly in the North Atlantic and for the AMOC, there's a lot of overlap between how sea ice forcing drives change and greenhouse gas forcing from the rest of global warming in the absence of sea ice loss drives change. And this, of course, extends to the Arctic itself as well, where we're really co-locating the forcing itself with the response. All right. So that's kind of where we're exploring right now. But we've been recently humbled by these new results coming from Alexandra's runs, right? So that's the way science works, I guess. You think you have a story, and then something else comes along to change your story. And so what he's found is that, in fact, you can see here, but quantitatively, that the basic test of linearity applied to the zonal mean temperature and zonal mean winds is not as strong in these runs as they are in the other runs. And we're not sure if that's arising from teleconnections coming from the Antarctic forcing that we're using, or the fact that the sea ice forcing is actually weaker in these simulations. So that kind of takes us to the end. All right. So in two of the models we looked at, Arctic sea ice loss and greenhouse radiative forcing drive additive and separable responses in the atmosphere. But the responses become less additive as we go into the Arctic and North Atlantic. Perhaps not surprising. But what this means is that, and why this is important, is that if we're trying to attribute changes, regional changes in storm track intensity, or trying to understand the coupled ocean atmosphere response, and we try to pin it on sea ice loss, we are actually challenged by these kind of results to really be precise about what we're saying, especially if there's lots of conditional issues depending on the model and the model experiment. And I mentioned these new results from WACM4 and PAMIP that we're trying to figure out right now. And really what this calls for is coordinating experiments across these different types of models, because we don't really know at this point whether the differences we're seeing and the non-robust aspects are coming from model protocol or from actual intrinsic differences in the models. So if the way we force sea ice is important, that could actually have a bearing on the robustness of these results, especially in the North Atlantic. Okay, with that, I believe I went over time, so sorry about that. I know you've been waiting patiently, so I'll stop there. Thanks.
Thanks, Paul. You got a couple of questions waiting for you in the chat. So Frederick Dupont's the first one. So I don't know if your phone, if your office is quieter, I don't know if you want to try asking it, Fred, or are you?
Oh boy. Yeah. Okay. Let's try now.
Yeah.
So sorry, Paul. I was still distracted by people around me at the beginning of your talk. So I missed. So how did you separate the sea ice loss from the greenhouse gases? Since obviously greenhouse gases are driving ice loss.
Yeah.
Trying to figure what you meant.
Yeah, so there's several different methods, and this has been reviewed in a paper by James Green and others in 2018. But in these two studies, in fact, different methods were used. So in CAN-ESM, what's done is it's a nudging. It's what they use in some of their seasonal prediction system experiments with a nudging applied to the sea ice to a target state. In CNRM, they used a different technique. It was basically a ghost flux. They just put in the forcing that would keep the sea ice either fixed at its value in year 2000 or pre-industrial rather, and then they would double CO2 but keep the sea ice sort of forced to stay in the cold state. In the recent, so Alexander and I just submitted a paper to James where we use a different kind of nudging methodology, which is a little gentler, and it focuses on nudging the thinnest ice enough to get kind of a target response in sea ice concentration, and then also adding in some basal heat flux to sort of keep the sea ice sort of thickness towards a target as well. And that combination, you have to, it's a little less artificial. We outline some advantages. So there are definitely a lot of choices in this, and both in a lot of, and this is one of the things we're struggling with here. So that's one of the bigger issues is how these different methods actually drive different types of simulation, different types of responses.
Is there a reason to separate ice loss from greenhouse gases?
The reason is more for physical understanding and for attribution, right? So of course not in a way, right? The sea ice is just part of the system, but there's an awful lot of experimentation where we see models that have very different responses, responses to climate change and different degrees of Arctic amplification. And these kind of experiments help us understand the sources of those changes, right? So we've used these experiments to understand some of the radiative and non-radiative feedbacks that are at work, to understand poleward heat transport responses, to understand aspects of the oceanic response, right? So it's sort of for physical understanding, and there are people who are also just interested in understanding how sea ice has affected mid-latitude circulation, right? This is kind of a popular question now. So the PAMIP also deals with that. It's the consequences of Arctic amplification. Not to say that sea ice loss is the only source of Arctic amplification, but you can trigger a lot of Arctic amplification by changing sea ice.
Okay, thanks, Paul. It's a very complete answer. And in fact, it was so complete that it answered the other question in the in the chat. So I guess at that point, I'd like to thank all the speakers again in this and the previous session. It was great to have such an interesting and varied collection of talks. And I hope we can get back together tomorrow. And please don't forget about the posters. Posters are important, and hopefully everyone has a chance to check them out. So depending on your time zone, either enjoy your afternoon coffee and the rest of your day. And if you're, further towards the east, enjoy your evening. And we will hopefully reconvene tomorrow. So thanks, everyone.
Thanks.
Thanks, everyone.